So I'm going to talk about safe machine learning with an application to autonomous driving. This is a joint work with Shaked Shama and Amnon Shashua. So the motivation of this work is autonomous driving. Autonomous driving today is a science project. It's very impressive, but it's still not a product. Our goal in Mobileye is to make it a product, something that can scale to millions of cars by 2021. So the question, how do we move from a science project into a mass production? Machine learning is amazing. In particular, end-to-end deep learning, when you want to solve a problem, you just define an input and output, throw all of this into some neural network, let it do many iterations of stochastic gradient descent, and voila, we have a product. So in particular, if we want to solve autonomous driving, it is very tempting to take the input video, to feed it into a neural network, and to let the neural network output steering wheel and how to step on the pedals. This sounds very exciting. It's very good for a science project. What I want to tell you is that this is a horrible idea if we want to really build a product. So if we want mass production, end-to-end deep learning is very, very problematic. The main reason is that machine learning is all about expectations. What is a typical behavior of the system? This is what we train for. This is the objective in machine learning. We train the expected loss over some population. It's fine in expectation. It's horrible in corner cases. So suppose that we train a deep network, and once in 10 to the 9 hours, once in billion hours, the deep network does something really, really stupid. And this leads to an accident. There are many, many questions. First, how to fix these corner cases, even if we can find them. So now what? You trained your deep network on millions of hours, and now you have one additional incident, which is problematic. What do you do? The second question is how even to validate this. So suppose that you think you have a very, very good model, but how can you validate that it will work and will not make a mistake even in corner cases? And this is a real problem. So a very simple theorem in statistics tells us that if we want to validate an event whose probability is p, then we need to see 1 over p examples. So if here the event is is a probability of an accident in 1 hour, then we need 1 over p hours to watch 1 over p hours just in order to find on expectation an even single case of a failure. Without this, we simply don't know the performance of our system. So if we're talking about autonomous driving, and we want p to be smaller than 10 to the minus 9, then we need billion of hours. This is a lot of hours. Maybe we can use simulators, but it can be shown that simulators have exactly the same problem, because how can you validate that the simulator reflects reality? So it's basically the same problem. And finally, even if you have a very good system and you are willing to let a validation process happen, the validation process itself may be very, very dangerous, because if you put a human driver behind the wheel, let him drive with an almost perfect system for a while, then the human will be bored and will not pay attention, and then when something will happen, the human will not be attentive to the danger. So all of this make the end-to-end deep learning approach problematic. What I'm going to describe you is our approach for autonomous driving, but it actually sheds some light on 3 techniques for making machine learning more safe. So the idea is to divide and conquer, to divide the problem into 3 components. This is a classic methodology in robotics. Sensing, planning, and acting. Sensing is understanding the present, planning is deciding what we want to do, and acting is actually doing it. And for each one of these components, we apply a different technique for making the machine learning process safe. For the sensing part, we use a high-level fusion technique to boost the accuracy of a system, and this is a generic thing that you can think about in your own problems and apply it in many, many cases. It's a very good approach. The second approach is to seal a machine learning process, the predictions of a machine learning process, to seal it by some formal model. Then you enjoy the benefits of the machine learning in the typical case, but you have some safety net that will save you from the problems of the machine learning in the corner cases. The third method, I'm not going to talk about it today, but we robustify a machine learning-based controller by using techniques from control theory. So I will talk about the first two things. Again, the sense, plan, act methodology. Sensing is understanding the present, is understanding what is around us. Planning is deciding what you want to do next. And acting is actually moving the steering wheel and the pedals in order to go to where we want. I will start with safety of sensing. So the goal here is to have negligible amount of safety critic sensing mistakes. A safety critic sensing mistake is, for example, there is a pedestrian in front of the car and you missed it. So this is a safety critic. Okay, another thing which is safety critic is that you think that there is a pedestrian in front of the car while you are driving fast, so you must brake very, very hard, but there is no pedestrian in front of the car. So this is also very, very dangerous. We want these events, these dangerous events, to have a very, very low probability of happening. The challenge, as I said before, is that machine learning-based sensing systems are far from this high bar. I'm not familiar with any machine learning algorithm that can give us a performance of 99.99999 times. Everything is with 9, okay? And even validating this system is very, very difficult. So here is a very, very simple trick in order to reduce the burden of validation and actually to build a reliable system. It's a very, very simple trick. Build 3 independent systems. And then it is not hard to see that if each system fails with probability of at most p, then just taking the majority vote among the 3 systems fails with a probability that scales like p squared. It means that if we need billion of hours to validate a single system, we only need 200,000 examples in order to validate this combination of 3 systems. Of course, you can generalize it further. So even think about just a camera. You want to detect vehicles. Now, this tractor on the side has a very strange shape. It is actually likely that some machine learning system will fail to detect it, unless they will see it. Now, if we are talking about an end-to-end system, we need to see it, but in a relevant position. And this is even more unlikely to happen in your data. But if instead you're looking for vehicles all around the vehicle, then the probability that you will have a safety critic miss is the probability of a miss on this particular vehicle times the probability that this vehicle is in a safety critic position. So you gain a lot by solving a little harder problem than what you need. So this is again an example why you don't want to use an end-to-end solution. Instead, you want to actually understand what your system is doing. Okay, so far this is one technique. Just build several systems and do some very simple majority vote or some aggregation of the system, thus getting a boosting of the accuracy of the system. The second approach is for the decision-making system. And here we have an even harder problem. The problem is that you cannot even try to guarantee a negligible amount of accidents for the decision-making process. Think about this situation. Suppose that the middle car, the yellow car, is an autonomous car, and the red cars are human-driven. Okay? And this is an everyday situation in Ayalon Road, right? We have more than 3 lanes. We are surrounded by humans. Each one of them is driving while doing something else, sending messages, drinking coffee, or whatever. Now, one of the drivers suddenly move into our lane. There is nothing the autonomous vehicle can do in order to prevent an accident. And if you think about it, roughly half the mistakes, roughly half the accidents might be due to mistakes of other drivers. Okay, so you cannot actually beat the statistics by more than a factor of 2, because half of the accidents are not your fault. Okay. So if we cannot guarantee safety in a strong manner, what can we guarantee? And one approach that the industry adopt is the statistical approach, end-to-end statistical approach. And the claim is that self-driving cars should be statistically better than a human driver. Okay? This can be achievable. But there are many, many problems with this claim. And it is wrong for many reasons. First, in order to validate this claim, we must validate it in an online manner. It's not like that we can collect data and then validate it, because everything here is a multiplayer game. So we want to validate with respect to how real drivers react to your policy. So it's not feasible to drive so many hours after every update of the software. Second, as we claimed to before, you cannot reach negligible amount of events, because the best thing that you can hope for is to reduce the number of accidents by a factor of 2. Okay? So it's not negligible. Finally, and this is, I think, a big deal in decision-making, this claim is not transparent. What will happen when a self-driving car will be involved in an accident, say, kill a little kid? Can we say, yes, we killed a little kid, but we are statistically better than a human driver, right? I don't think that the society will agree to this claim. People look not at statistics, but on the type of mistakes we are making. And we need to be very clear about what type of mistakes our model is going to make. And this led us in Mobileye to an alternative approach to safety. And this is a formal model. So we define a model which we call responsibility-sensitive safety. As its name indicates, it is all about responsibility. So we want that self-driving cars will never be responsible for accidents. What does it mean to be responsible for an accident? It either means that you caused the accident, or it means that somebody else might have caused the accident, but you didn't respond properly to the dangerous situation. So RSS is a mathematical, interpretable model that formalizes common sense. The common sense of what does it mean to be in a dangerous situation. What should be the proper response when you are at a dangerous situation? And as a result, who is responsible for an accident? And the idea is to set the rules of the game in advance and not at the aftermath of an accident. So due to the lack of time, I will skip RSS principles, and I will go directly to 2 criteria for a good formal responsibility model. So one of them is soundness. You want that if the model says that you are not responsible for an accident, then it will match the common sense of all of you. And secondly, you want the model to be useful, because you can put the responsibility on the AV car all the time, and the result is that the AV car should stay in the garage. It is very safe, it is very sound, but it is not very useful. So you need to balance the usefulness and soundness trade-off, and this is something that we are doing. So again, I'm skipping the actual model, and I would like to talk about this approach of RSS versus the statistical approach of saying that the model the AV car should be statistically better than a human. So the advantages of RSS is that it is transparent. We can explain to the society exactly what does we mean when we say that the autonomous vehicle is safe. And also from economic point of view and practicality of the approach, we don't need many hours of validation because we have the model. And this is actually a big advantage because the process of validation itself is very, very dangerous. A possible disadvantage of this approach of having a model is how to show the completeness of the model. So the model say that in many situations that it took into account what is the right response and what you should do. But what will happen when we will encounter a situation which is not covered by the model? Okay, this is a big problem. So our approach to tackle the completeness question is to use accident data, to use data in order to validate statistically, but just the completeness part of the model. In particular, we took a data of 6 million car accidents, and we made sure that the model covers all of them. So you get statistical claim, but it is very, very strong. Okay, so if we are using RSS, we don't need machine learning at all? The answer is, of course not. RSS gives us a safety net for learning-based driving policy, but the decision-making itself, in order it to be useful and in order it to be comfort, is relied on the powerful techniques for machine learning. In particular, we use MCTS learning, similar to AlphaGo. We use value-based reinforcement learning for short-term decision-making, and we combine deep learning with robust control in order to translating the kinematics of the trajectory into pedals and steering wheel. So we use the benefits of machine learning, but we have a model which gives us a safety net. And again, this is a general technique. Use the machine learning as a recommendation, not as actually what you are going to do. So combine sophisticated decision-making of machine learning with something very, very simple that need just to tackle the corner cases. So this is the second approach. Now I would like to show you a little demonstration, if we can start the video. This is a demonstration of our car.
What you will see here is a merge in a dense traffic scenario that will be followed by a lane change. Now, as the AV approaches to the end of the merging lane, an assertive maneuver is required in order to merge on time without affecting the flow of traffic. The AV is maneuvering under the assumption that the car behind it, which is a white commercial vehicle that you will soon see in the rear-view camera, will slow down, just like a human driver would do. Once the vehicle detects an adequate gap, the car is confidently yet safely decides to change lane. The next lane change that you will see happens in a situation where the adjacent lane is moving faster than the one the AV initially occupies. This is why the AV decides to change lane, and once it identifies a proper gap, it initiates a nimble maneuver to overtake the slow-moving traffic. This is happening while giving way to the car that is cutting in front of it. What you will soon see here is a slow-moving tractor in the leftmost lane. All the vehicles are looking to overtake it at the same time at the same place, and this is creating a very complicated driving scenario even for a human driver. Using the turn indicators is just not enough, so the AV has to signal other vehicles its intent by hugging the lane marker, indicating that it wants to merge. Once a gap is identified, the AV takes the opportunity and merges in front of the Jeep tailgating it, which is trying to overtake the tractor at the same time. Here, the AV identifies a slow-moving truck down the lane and decides to overtake it. The AV is signaling the car behind it by nudging toward the adjacent lane until the vehicle behind it gives way, making room for a safe overtake.
All right, thank you. So as you saw, decision-making in autonomous driving is very, very complicated, and we need machine learning for it, but machine learning alone is not enough. So what I tried to show you is several techniques for how to combine machine learning with safety. One of them is to use redundant system in order to boost the accuracy. Another one is to have a formal model that gives a safety net for the decision making of the machine learning. Thank you very much.